Hello everyone. Today we'll be providing supplemental information about motors and how they can be used and analyzed in the construction of robots using the VEX IQ Robot Kit.
Electric motors are motors that take electrical energy and turn it into mechanical energy. This conversion happens due to electromagnetism, meaning a force is applied when an electric current is present. This force causes a torque to be applied to the motor shaft, which causes the wheels to spin. There are a few basic physics equations that apply to motors. The first has to do with the power. Electrical power, also known as P in, is converted to mechanical power, also known as P out. But it is not completely equal, for there are forces of resistance, such as frictional force or other external forces, which cause a loss in power, which is also written as P loss. Electrical power is equal to mechanical power plus the power loss. Another important equation is the equation for mechanical power. It is simple. The mechanical power is equal to the torque times the angular speed. In this case, torque is written as m, for it is a moment force, and the angular speed is written omega rad.
Now we will show you how you can use motors in your robots. As you have most likely heard in our previous videos, the force that describes the actual motion of the robot is due to friction. What causes the rotation of the tires and the acceleration of the robot are the motors. The robot's motors do this by converting the electrical energy of the robot into mechanical energy, or more specifically, rotational energy. Picture a cyclist racing the streets of Windhoek. The tires turn due to the downward mechanical force of your foot, and from there, the wheels exert a force on the ground that launches it forward as a result of friction. That still applies, but instead of a mechanical force being applied to the pedal, the shaft of the motor sends power to the wheels, causing them to turn as a result of electrical energy instead of mechanical energy.
The two main types of motors are DC motors and AC motors. AC motors stands for alternating current, while DC motors stands for direct current. Most robotics kits use some sort of DC motors, while AC motors are usually used for more advanced robots. If you want to look more into the differences between the two types, we have provided additional resources on the website and in the downloadable version of the script.
In order to quantify the properties of robots, engineers and roboticists measure the two quantities of the robot and motor, and those are rotational velocity and torque of the motor. Unlike linear velocity, the velocity on the motor is like rotational velocity, which is the number of times an object rotates during a certain period of time. The rotational velocity is most often measured in terms of revolutions per minute, or RPM, which is how many times the system completes a full circle in a minute. The torque of a motor is a measure of strength, since motors provide rotational motion to the robot. As described in previous videos, the torque is the product of the force applied by the distance or length of the arm. Once motors have been designed by engineers, they are most often measured in terms of the power they deliver. In the case of motors, the power is the product of the torque and the rotational velocity, also known as the angular velocity. Now we will provide an analysis of motors through calculations and give recommendations on how to incorporate motors into your lessons for the students. The motors in the kit come in different sizes for the students, so one way you can help them gain some problem-solving skills is by helping them pick which size motor they should use for their specific need. Whether you want the robot to move across a flat surface or up an inclined plane is up to you. For the case of the problem, the robot will be moving up an incline of 10 degrees and will weigh approximately 25 pounds or 11.36 kilograms. It is also previously noted that the robot can reach a maximum speed of 1 foot per second in 2 seconds by accelerating 0.25 more meters per second. The diameter of each wheel is 6 inches, meaning the radius is 3 inches or 0.0762 meters each. The robot will start from rest, and from there it will accelerate up the incline at full speed. The vertical forces that act on the robot are the force due to gravity and normal force, which is the upward force on the wheel. Since the wheel is rotating, the torque of the wheel will be represented as the product of the force of the wheel and the radius, which is 3 inches long. In this case, the sum of the forces acting on the robot will equal the total mass multiplied by the acceleration. In order to figure out the formula for force, we'll designate if the forces are positive or negative. Since the normal force on the wheel is positive, that force will be positive, meaning that the downward force due to gravity will be negative, and these sums of forces will equal the mass times the acceleration, which is the actual movement of the robot. From there, we can arrange the formula to isolate the force on the wheels, which equals the sum of the mass and acceleration and the force due to gravity. The force on the wheel can be arranged as the quotient of the torque and the radius. Since the robot is on an inclined plane, the mass due to gravity is represented as the mass and gravity times the sine of the angle. Through proper rearrangement, one can see that the torque is equal to the product of the mass and the radius of the wheel by the different accelerations, specifically gravity and that of the robot. By plugging in the values, one can see that the torque is 1.69 Newton meters or 14.97 inches per pound. Although this is the torque on the wheel, this is also the torque required to drive the robot, specifically to turn the wheel. In order to overcome this torque, you can use one or multiple motors. For example, if you use two motors, each motor needs a torque of 6.5 inches per pound.